Okay, so now we're going to look at phase changes and heat of transformation. And let's remind ourselves what a phase is. And for that, let's go back to this simulation here. And so here we have neon at 13 Kelvin, and it is in a solid phase. And you can see all the particles are arranged in an orderly fashion, and you can see they vibrate, but they kind of stayed around the same place all the time, right? Let's look at a liquid phase for neon. And this is a liquid phase. The particles are still very close together, but now they move around. They are not attached to any particular place. Look at the solid in case. If you look at this particle here, for instance, look at this one particle here, right? It always stays around that same place. If you go if you look at the liquid phase now, the particles they just move around. They are not completely organized. And let's look at the gas. In the gas phase, well, they are all over, right? And they are far away from each other and they hardly interact. So this is the liquid phase and this is the solid phase. Gas phase, liquid phase, and solid phase. Let's look at another element, let's say argon. And here, this is 43 kelvins, and you can see again, this is a solid, and the particles vibrate. That vibration is the energy, gives the thermal energy of the system. They vibrate, but they don't move much. They always stay around that side. Now here in the liquid phase, you can see that they are close together, but they move. They are not attached to a particular site. And then the gas phase for argon. Let's look at oxygen. Oxygen, this is the gas phase for oxygen, and you can see, well, oxygen comes in O2. You don't find an oxygen atom by itself. You always find them as O2. Let's look at the liquid phase of oxygen at 69 kelvins. This is the liquid phase, and the solid phase for oxygen. So right there. Let's look at water. Water is interesting. This is ice, and then let's look at just liquid water. And you can see one interesting thing about water, if we look at the phase diagram, uh, we'll look at the phase diagram in a little bit. But one interesting thing about water is that the solid phase occupies more volume than the liquid phase. So the density of the solid phase is less than the density of the liquid phase. This is water vapor, got the gas phase, and you can see how it looks. Let's look at the phase diagram. So the phase diagram in a temperature versus pressure give you the values that you need. For instance, if you have a pressure in this range here, if you have a pressure in this range, well, then you always have a solid. But if you have a temperature and a pressure in this range, you'll have a liquid. And if we have a pressure and temperature in this range, you would have a gas. For instance, let's increase the pressure. If we increase the pressure here and right there, then I have moved the system to somewhere here, decrease the pressure. And let's look at water here. So, and compare the phase diagram of water with neon. And this line here, this line for neon has a positive slope. For water, has a negative slope that reflects the fact that ice is less dense than water. Okay, so let's go back to the slides and go through all the important points that we need to cover. So we know, we remember now what a phase is, and a phase change is, well, when you go from solid to liquid or from liquid to gas, and is characterized by a change in thermal energy. So the way to produce a phase change is by heating the system or by removing energy, thermal energy from the system, by cooling down the system. That amount of heat that you need to cause a phase change is called heat of transformation. And we normally denote that with an L. That is the heat of transformation. And and if you have a system of mass m, then the total heat that you need to produce a phase change is m, the mass times the heat of transformation. The heat of transformation is the energy that you need to cause 1 kilogram of that particular material to undergo a phase change. So, question here, if you heat a substance in an insulated container, is it possible that the temperature of the substance remains unchanged? Take a minute to think about this question. And the answer is yes. If you heat a substance, if you heat a solid, at some point the heat that you're adding to the solid is going to be used to break the bonds that make the solid, and the temperature of the solid as a whole is not going to increase until the whole phase change is produced. So if there is a phase change, whenever there is a phase change, you are adding heat to the system, but you won't be increasing the temperature. So how do we represent that in a graph? Well, here we can plot heat versus temperature. And then we see that we have in the solid phase, we're adding heat, and as we add heat, the temperature is increasing. When I get to the phase change, to the phase transformation, I'm going to be adding heat, but the temperature is going to be the same. So what I'm doing during this period is I'm basically breaking the bonds and producing the phase change. So that energy is used not to cool the system, not to heat the system and increase the temperature, but to produce a phase change. Then um, after I've broken all the bonds here, then I can start increasing the temperature. So the temperature is going to increase until I get to the next phase change, which is the boiling phase. And at that point, I'm going to be adding heat, but the temperature is going to remain constant. And then again, I'm going to be adding heat, and the temperature is going to be increase. How much heat do I need here? Well, I need m, the mass, times the heat of fusion, that much here. And in this case, I need m times the heat of vaporization. So this table shows some melting boiling temperatures and heats of transformations for nitrogen. The melting temperature is minus 210 Celsius, and this is the heat that you need to add to melt nitrogen in joules per Kelvin. And this is the heat of vaporization, and this is the temperature at which that occur. For water, we all know this, 0 for the melting temperature, and this is the heat that you need to add. And notice that it's way bigger than the others. You need a lot of heat to transform ice into water. And here, this is the heat of vaporization for water, and this all is at 1 atm. And this is the amount of heat that you need to make water into vapor, into gas. So and compare again, this is 22.6, and compare that with the others. So we have alcohol, mercury, and lead also in this table. Now, let's talk about calorimetry. And calorimetry is basically the study of heat transfers. We're going to have two systems, and we want to look at how we transfer heat from one system to the other. So we're going to to start with, consider two systems, system 1 and system 2. And then these are going to be inside a thermal here. This is insulated. There's no heat entering or leaving this volume here. So let's assume system 1 is at temperature T1, system 2 is at temperature T2, and we can assume that T1 is greater than T2, just for the sake of argument, right? Let's assume this is greater than this. Then there's going to be, we know there's going to be some heat moving from T1 to T2. And the amount of heat that moves from T1 to T2 is the heat that T2 receives. So there's going to be some heat leaving T1, that is Q1, right? And there's going to be some heat entering T2, that is Q2, and Q1 is equal to minus Q2 because there's no other way where that energy can go. So the absolute values of those quantities are the same, and this equation is the relevant equation. The Q1 plus Q2 has to be equal to 0, which is the same as here. But this is not only true for one system. If I have more system here, if I have a system 3, 3, and if I have a system 4 here, then I can have heats moving in from, and this is at a temperature T3 and a temperature T4. Then I'm going to have heat moving from T1 to T3, from T1 to T2, from T2 to T1, and so on. So I'm going to have all kinds of heat. So I can write that the heat transfer to system I, the heat transfer, say, to system 2 would be equal to the heat transfer uh, from 1 to 2, from 1 to 2, from 3 to 2, from 4 to 2, and so on. So this equation is valid, and this sum here, when you add the heat added to 2, for instance, let's assume that I have 4 systems. So there is the heat Q1 plus the heat Q2 plus the heat Q3 plus the heat Q4, right? So these are the heats that are added or removed from system 1, system 2, system 3, and system 4. Because the heat there's no heat coming in or out this whole air system, this has to be equal to 0. And this is the main equation that we have to think of when we solve calorimetry problems. Okay, let's go through this question here. We have 50 grams of ice at 0 degrees, and we add that to 50 grams of liquid water at 0 degree. The container is insulated and also at 0 degree. After a while, will you have all ice? Would you have more ice and less water? Would you have the same 50-50? Would you have less ice and more water? Or would you have all liquid water? Take a minute to answer the question. Well, there's no temperature changes here, so there's no heat transfer, so you're going to stay at the same place. So we're going to be solving calorimetry problems, and these problems are fairly simple. You need to identify your systems. That's one thing that you need to do. And then you need to list the information that you know about your system. So this is the main equation that we're going to be using. And then for systems that undergo a temperature change, Q is equal to the mass times the specific heat times the temperature difference. And this could be positive or negative. If this is positive, that means uh, heat is leaving the system. If this is negative, heat is entering the system. Be sure to have the temperatures Ti and Tf in the correct order. That's very important. This is what's going to give you whether the temperature is leaving or entering the system. Systems that undergo a phase change would just get this much, m times the heat of vaporization or fusion. And then you need to, this sign here depends on whether the system is going from solid to liquid or from liquid to solid, or from liquid to vapor or from vapor to liquid. And some system may go through both types, may increase the temperature and have a phase change. In that case, you need to add the heats. So let's look at a simple problem here. We have three interacting systems. So have a 200-gram piece of iron at 120 degrees, 150 grams copper at minus 50 degrees, and all this is dropped into 300 grams of alcohol at 20 degrees. What is the final temperature of the system? Well, we have three systems here, so we cannot use this equation for two systems. So what we need to do use is the main equation that says that the heat for the iron plus the heat from the copper plus the heat for the alcohol, all that have to be equal to zero. What is the heat for the iron? Well, it's the mass of the iron times the specific heat of the iron times the change in temperature, which is the final temperature of the iron, minus the temperature at which the initial temperature of the iron, which 120 degrees, plus the mass of the copper times the specific heat of the copper times the difference in temperature, which is TF minus, and notice the two signs here. This is important, okay? And here you could have kelvins or degrees Celsius, it doesn't matter, as long as you are being careful with these signs. And finally, we have the heat for the alcohol, which is the mass of the alcohol times the specific heat of the alcohol times the temperature difference, the, uh, uh, the final temperature minus the initial temperature of the alcohol. From this equation, we can solve for the final temperature. We can put our values here, and we know these three numbers. We have them from the table. We know the masses, and we can solve this, and we get that this is 27.7 degrees Celsius.